Let's say if we're trying to divide these two polynomials together, how will we do this using synthetic division? So synthetic division, you can kind of imply that it's just a method of dividing two polynomials together. And the requirements for synthetic division to work is that you're dividing something with an x term and you're dividing something that's a constant term, right? So just a single number. So if you have something in the form of x minus some sort of constant, so a term without an x, well, that means that you can use synthetic division. For example, if I was dividing this polynomial by, let's say, x squared minus 4, you'll notice how this does not match the form x minus c, right? Because it has an x squared term instead of x term. So I cannot use synthetic division to divide this. If I had something like 2x minus 4, I can't use synthetic division to divide this because it's not in the form x minus c, right? You'll notice how the x term is just x. It's not x to the second power. It's just a singular x and has a coefficient of 1. So it's the singular x, nothing raised to the second power or above. So that's the requirements for using synthetic division. It has to be to the first power, and there's only one of the x. So what you're going to do is you're going to look at all the coefficients of these terms. So if you look at the numerator here, you're going to place all the coefficients of the terms inside kind of this division box, right? So in this case, my highest term is x to the third power, and the coefficient of that is 1. My second highest term, x to the second power, has a coefficient of 5. My third highest term is 6x, has a coefficient of 6. And my constant term, you can think about it as x to the 0th power, right? So you notice how everything I'm listing inside the box is in like a decreasing x order. So this 8 right over here, I'm going to put in the box. Now you're going to take a look at your denominator, what you're dividing by. And you're going to ask yourself, what makes this equal to 0? So what number can I put into x that makes this thing equal to 0? In this case, if you put in a -2 for x, well, that's going to make this equal to 0, right? That's going to make the denominator equal to 0. So that's what I'm going to put to the side. All right. I'm going to put this line beneath. I'm just going to put this addition sign. All right. So the first step is you're going to take your highest term, right? And you're going to bring it down. So you're going to put a 1 down here. Now you're going to multiply this 1 by -2. So 1 times -2 is going to give you -2. And you're going to bring it up to this box. Now what you're going to do is you're going to add these two terms, right? That's why I have this addition sign over here. So 5 plus -2 gives you 3. And now I'm going to multiply 3 by -2. So 3 times -2 gives me -6. And you notice I'll put this -6 right over here. 6 plus -6 gives me 0. Now I'll multiply 0 by -2, and I'll just get 0. Finally, 8 plus 0 gives me 8. Now you might be wondering, what are these numbers used for? And they represent the coefficients of our new kind of polynomial. So in this case, if I divide x to the third power by x to the first power, I'm going to get x to the second power, right? So this resulting polynomial is going to be 1x to the second power plus 3x plus 0. And then this 8 right over here represents the remainder. And to express the remainder, what you do is you place the remainder on the top. So you're going to make this a fraction, okay? You're going to place the remainder on the top. And then after that, you're going to put the thing you're dividing by on the bottom. So it's going to be 8 divided by x plus 2. And that's your answer. Right, so you notice how all of these right over here represent the coefficients of my new polynomial. And then after that, this remainder, the remainder is always on the most right-hand side of this thing. And you just write it in the form of, the remainder divided by whatever you're dividing by. Now, once again, the first step is, well, you put these things inside a box, right? You put the coefficients inside a box. So in this case, my x to the fourth term, my highest term, is going to be 2. My second highest term, x to the third power, is going to be 3. Now here's the tricky part. Notice how I don't have an x to the second power, right? And remember in the last question, right, you notice the order, right? It went from, in the last question, we went from x to the third power to x to the second power to x to the first power and then x to the 0th power. However, in this case, we kind of skip the x to the second power. So right over here, what I'm going to do in the box is I'm going to put a 0 here. Because this polynomial can be rewritten as x to the 4th power plus 3x to the 3rd power plus 0x to the 2nd power plus 4x plus 5. And you notice how the coefficient of the x squared term is 0, which is why we put a 0 inside the box. Right, so whenever you're doing synthetic division and you're putting the coefficients inside this division thingy, always make sure that you're never skipping out a term, right? The term you're putting in, term you're kind of going down by is always going to be 1, right? You notice how it went from 4 to 3 to 2 to 1 to x to 0, right? And in synthetic division, you're never going to skip a term. If there's no term, like in this case, if there's no x to the 2nd power visible, you're going to put a 0 in for that place where it would go. So in this case, my third highest term is x to the 2nd power, but since I don't see that, I'm going to put a 0 inside this box. This term, the coefficient is 4, and then I'm left with 5 as my constant term. In the outside of the box, you put in what makes the denominator equal to 0. So what makes x plus 1 equal to 0? Well, that's just going to be -1. Now I'm going to divide. So I'm going to place this thing on the bottom. I'm going to place this addition sign, and let's go. I always bring down my first term. So I'm going to bring down the first term. Now I'm going to multiply it by the -1. 2 times -1 is going to be -2. I'm going to add these two numbers together. 3 plus -2 gives me 1. Multiply this by -1. I get 1 times -1 is just -1. -1 plus 0 is going to be -1. -1 times -1 is going to be just 1. 4 plus 1 is going to be 5. 5 times -1, that's going to be -5. And 5 plus -5 is going to be 0. So for my answer, I'm going to get, well, first of all, if I divide an x to the 4th power by a singular x, I'm going to get x to the 3rd power, right? I'm going to get x to the 3rd power. So this first term right over here, this 2, the first term, is going to be 2x to the 3rd power, right? Because if I divide x to the 4th by x, I'm just going to get x to the 3rd power, right? So in this case, this 2 right over here represents the highest power, right? The number that's the most left, the leftmost number, that represents the highest power. And then after that, you just go in decreasing powers. So in this case, this next term is going to be 1x to the 2nd power. This next term is going to be minus 1x, right? So you have this -1 coefficient. This 5 represents the constant, so it's just going to be 5. And the 0 right over here represents the remainder. If my remainder is 0, I don't have to write anything here, right? In the last problem, because our remainder was not 0, well, I had to write it out. But in this case, my remainder is 0. And if the remainder is 0, you won't have to write it out. So my final answer is 2x to the 3rd power plus 1x to the 2nd power minus 1x plus 5. So once again, I'm going to create this little box, and I'm going to put the coefficients of every term in. So in this case, we start off with our highest term, that's 3. Our second highest term's coefficient is 4, right? And now it looks like we skipped an x term. And we said that whenever we skip a term and, it's not visible here, we put a 0 in for the spot, right? We can think about this equation as 3x to the 3rd power plus 4x to the 2nd power plus 0x, right? So as a coefficient of 0 plus 5. So I'm going to put a 0 there. And then our final term, our constant, is going to be 5. I'm going to draw the line underneath. I'm going to put an addition sign. And let's go. Actually. And now, once again, right, we have to look at what makes the denominator equal to 0. So what makes x minus 3 equal to 0? Well, if I plug in a 3 for x, I'm going to get 3 minus 3, which is equal to 0. So on this top left part, I'm going to put a 3. I'm going to bring down the first term. 3 times 3 is going to be 9. Now I'm going to add these two terms together, so I'm going to get 13. Now I'm going to multiply the number on the bottom by the number I put there. Now what I'm going to do is I'm just going to multiply this 13 by this top number 3. So 13 times 3 is 39. 39 plus 0 is going to be 39. Then I'm going to multiply it again by 3. So then I'm going to get 39 times 3, and that's going to be 117. 5 plus 117 is going to give me 122. So now I have my coefficients. Now it's time to write out the polynomial. So remember, if I divide something to the third power, in this case, if I divide x to the third power by an x term, right, the highest power to the term on the bottom, which is always x to the first power, I'm going to get x to the second power, right? So in this case, right, this coefficient represents the x to the second power term. So it's going to be 3x to the second power, right? And you notice how when I divide my polynomial by this x term, the resulting first term is always going to be 1 power lower than when it started. Plus 13x, right? Plus 39, right? We always go down by 1 unit, right? So this is x to the first power, this is x to the 0 power. And finally, because we have a remainder, what we do is we create a fraction, right? Where the remainder goes on the top, and then after that, whatever you're dividing by goes on the bottom. So this is our final answer. So you know how, like I said, that if you have something like, let's say 2x, this polynomial divided by 2x minus 4, that I said that we can't really do that because, you know, it's not in the form of x minus c, right? I can't use synthetic division for this. Well, it turns out that, yeah, you can't use synthetic division, but there's actually another strategy, polynomial division. And the good thing about polynomial division is that, unlike synthetic division, there's basically no restrictions. You can divide this by x squared minus 10. You can divide it by basically anything. It's not 0. The first steps are pretty similar. You're going to put the thing you're dividing by, you're going to create the division box, you're going to put the thing you're dividing by on the outside, and then put the thing that you're dividing on the inside. So I'm just going to place everything on the inside. Okay, now the first step is you want to take a look at the first term of what you're dividing by. And you're going to take a look at the first term of, you know, what you're dividing. So in this case, I'm going to take a look at this 2x and this 2x to the third power. I'm going to ask myself, what number multiplied by 2x gives me 2x to the third power, right? What multiplied by 2x gives me 2x to the third power? And the answer to that is x squared, right? If I multiply 2x times x squared, I'm going to get 2x to the third power. And what I'm going to do is I'm going to distribute this x squared to all of my terms. So in this case, if I multiply x squared by 2x, I'm going to get 2x to the third power. And if I multiply x squared by 4, I'm going to get a negative 4. If I multiply x squared by negative 4, I'm going to get minus 4x to the second power. Now what I'm going to do is I'm going to do subtraction, right? Just how you would do in like a normal division problem, right? You would subtract, right, these two terms. So in this case, I'm going to subtract all of these terms together. Right? I'm going to subtract 2x squared, 2x to the third power minus 2x to the third power. I'm going to get 0. And 4x to the second power minus negative 4x to the second power. Well, negative makes positive. So I'm just going to get 8x to the second power. So once again, now we end up with 8x to the second power. You're going to bring down, right, the term next to it. It's just like, it's kind of similar to like a normal division problem, right? Where like you bring out like the next term after you subtract. So every time you subtract, the things together, right, you're going to bring down the term that's after it. Now I have 8x to the second power plus 8x. And now what I'm going to do is, once again, I'm going to repeat the same process. I'm going to look at the first term right over here. I'm going to look at the term right over here, right? First term right over here. I'm going to ask myself, what multiplied by 2x gives me 8x to the second power? And the answer to that is 4x, right? 2x times 4x gives me 8, right? 2 times 4 gives me 8, right? And x times x gives me x to the second power. I'm going to distribute this 4x to these two terms. So I'm going to get 4x times 2x. We've already established that this is 8x to the second power. And 4x times negative 4 is going to be negative 16x. So once again, I'm just going to subtract both of these things together. These cancel out, right, because they're the same thing. And 8x minus 16x is 24x. And then now you're going to bring down the next term. Once again, you finally repeat this process one last time. So in this case, I'm going to ask myself, what multiplied by 2x gives me 24x? And then in this case, the answer is going to be positive 12, right? 2x times 12 is going to be 24x. And now I'm going to distribute the 12 to these two terms. 12 times 2x is going to give me 24x. And 12 times negative 4 is going to be negative 48. So I'm going to subtract these two terms. These two terms cancel out. And 10 minus negative 48 is going to be 58 because two negatives make a positive. Now, when you're doing this strategy, if you're ever left with just a whole number without an x, well, this represents your remainder. So your final answer is going to be x squared plus 4x plus 12. And then remember how to write a remainder, right? What we do is we create this fraction. The remainder goes on the top, and what you're dividing by goes on the bottom. This is going to be our answer. Now let's say we have 2x to the third power minus 9x squared plus 15 divided by 2x minus 5. Do the same strategy. We place the numerator inside. Place the numerator on the inside. But, here's the tricky thing. So just like synthetic division, right? You notice how we go from x to the third power to x to the second power, and then we skip the x term, right? Because there's 0 of the x term. So that's exactly what we're going to put inside the division side, right? If you don't see an x term, right, if it kind of skips it, well, that means just put a 0 in for that place. Plus 15. And we divide this by 2x minus 5. Ask yourself, right? The first term of this is 2x, and the first term of this is 2x to the third power. What multiplied by 2x gives me 2x to the third power? And the answer to that is x squared. So once again, I'm going to distribute the x squared to these two terms. 2x times x squared is going to be 2x to the third power. And x squared times negative 5 is going to be negative 5x squared. I'm going to subtract these two terms. These two terms cancel out because they're the same. And negative 9x squared minus negative 5, so two negatives make a positive. So it's like negative 9x squared plus 5x squared, which is negative 4x squared. Bring out the 0x. So now, once again, ask yourself, what multiplied by 2x gives me negative 4x squared? The answer to that is negative 2x. So negative 2x times 2x gives me negative 4x squared. And then I distribute the 2x, negative 2x. So these two things multiplied together give me negative 4x squared. And negative 2x times negative 5, that's going to be 10x plus 10x. So I'm just going to subtract all these terms. I'm just going to be left with, well, these two things cancel out. I'm just going to be left with a 10x term, right? Okay, and now, once again, you can't forget the negative sign, right? Because 0x minus 10x is just going to be negative 10x. So don't forget that. Bring down to 15. And then what times 2x gives me negative 10x. Well, that's just going to be negative 5. Negative 5 times 2x is going to be negative 10x. And then after that, negative 5 times negative 5 is 25. However, I have to subtract this. Sorry, there's not much space. But 15 minus 25 is negative 10. And if we're just left with a number without any x's, that's our remainder. So our final answer is x squared minus 2x minus 5. And then once again, to do the remainder, you create a fraction. The remainder goes on top. Thing you're dividing by, in this case 2x minus 5, goes on the bottom. And that's our answer. Now, the factor theorem states that if x minus c is a factor of f of x, then f of c is equal to 0. So basically, if I have f of x is equal to x squared plus 5x plus 6, and I tell you that x plus 3 is a factor of this polynomial, then if I plug in f of negative 3 into this equation, well, I'm going to get 0. This looks confusing at first, but this just comes back to like the idea of factoring, right? Remember, we can factor this x plus 3 times x plus 2. And now, right, if we plug in, you'll notice how if we plug in negative 3 in for x, well, negative 3 plus 3 is 0. So f of x is equal to 0 when you plug in, right, kind of the you notice how if I plug in negative 3 in for x, well, negative 3 plus 3 gives me 0, and 0 times whatever this is 0, right? And likewise, if I tell you that x minus 2 is a factor, if I tell you that x plus 2 is a factor of this polynomial, that means that f of negative 2 is equal to 0, right? And you notice how when x plus 2 is a factor of my polynomial, when I plug in the opposite of that, negative 2, well, negative 2 plus 2 is just going to be 0. And 0 times whatever this is going to be 0, right? So this just comes back to the idea of factoring, right? You plug in the opposite of what's inside the factor thing, and then you're going to get 0. Now, the factor theorem is important because it shows that if you have a polynomial f of x as a polynomial, and x minus c is a factor of it, that means that when you divide f of x by x minus c, you should get no remainder. So you should get a remainder of 0. So that's important. So for example, right, let's say if I have x squared plus 5x plus 6, and I divide this by x plus 3, and I tell you that x plus 3 is a factor of x squared plus 5x plus 6. Well, that means that when I divide these two things together, I expect to get no remainder. And that's true, right? If I factor x squared plus 5x plus 6, I get x plus 3 times x plus 2, and then all of this is still divided by x plus 3. And you notice how the x plus 3, they cancel out. So you're just going to be left with x plus 2. Right? So this is the reason why it's important, because if this is a factor of this larger polynomial, then you can somehow factor the larger polynomial so that, the factors cancel out. If I tell you that I have this polynomial and I divide it by x minus 1, I want you to prove that x minus 1 is a factor of this larger polynomial. Well, in this case, I'm going to use, because there's not really a clear way to factor this top expression, since, it's to the third power, one method you can use is synthetic division, right? So once again, I'm going to place all the coefficients inside this box. So we have 1, we have negative 6, we have 11, and we have negative 6. And then after that, what makes the denominator equal to 0? Well, if I plug in 1 for x, that's going to be 0. So 1 here. I'm always going to bring the 1 down, right? Always bring the first number down. I multiply these together, so I get 1. I add them, so I get negative 5, right? Negative 6 plus 1 is negative 5. I multiply again, so I get negative 5. Add these two things together, I get 6. 6 times 1 is 6. Add these two together, I get 0. And now you notice how my remainder is equal to 0. And that basically tells me that, and this remainder kind of tells me that x minus 1 is a factor, okay? So if you're dividing large polynomial by the smaller thing, and when you divide it, you get no remainder, well, that means that it's a factor of it. And in this case, right, so in this case, if I actually write this down, I'll get x squared, this negative minus 5x plus 6, right? Because when I divide x to the third power by x to the first power, I'm going to get x to the second power, right? Now you can all agree that if I said that this big polynomial divided by this smaller polynomial gives me x squared minus 5x plus 6, well, that means that if I multiply these two things together, I should get back to where I started, right? So it's like saying that, like, if 18 divided by 6 gives me 3, then 3 times 6 equals 18, right? This is basically what I'm saying, right? This thing divided by x minus 1 gives me this, which means that these two things multiplied out together should equal what I had originally. So if I said that f of x is equal to x to the third power minus 6x to the second power plus 11x minus 6, well, that means that f of x is also equal to what's down here, right? Now, if I was asking for like the fully factored form of this function, well, what I can do is notice how two numbers that multiply out to be positive 6 and add up to be negative 5 are x minus 3 and x minus 2. And we don't forget the x minus 1. So that means that if we want to factor this polynomial completely, well, all we have to do is, first of all, we can use synthetic division. We get one of the factors, right? Get one of the factors. And then after that, for the other kind of part of the polynomial, you could just factor it. Or you can use the quadratic formula. The polynomial remainder theorem tells us that if you want to find out the remainder of f of x when divided by x minus c, just plug in f of c and your result will be the remainder. If I have a polynomial like this, x squared plus 4x plus 7, this is f of x. And we want to find out what is the remainder of this polynomial when I divide it by x minus 3. Now, obviously, one method to do it is synthetic division. However, just a quicker way to do it would be using this theorem. And this theorem basically tells you if you want the remainder of this polynomial when divided by x minus some number, well, all you have to do is just plug in the opposite of that number. So in this case, if we want to find out if x minus 3, what's the remainder of this polynomial when you divide it by x minus 3, well, we would just plug in the opposite of 3 into this polynomial. So I'm gonna find out what f of 3 is equal to. What's f of 3 equal to? So in this case, f of 3 is 3 squared is 9 minus 4 times 3 is 12 plus 7. And this is going to simplify out to 4. And this 4 tells me that, well, if I divide this polynomial by x divided by 3, x minus 3, I'm going to get a remainder of 4. That's all it's telling us. If let's say I wanted to find out what's the remainder when I divide this polynomial by x plus 5, well, I would just plug in the opposite of 5, in this case negative 5, into this polynomial. So f of negative 5 would be equal to negative 5 squared is 25 plus 20 plus 7. So then I get that that's going to be equal to 32, and then that's going to be 52. And this 52 just tells me that that's the remainder. So let's say that if f of x is this function, and I want to find out what happens when I plug in x minus 2 into this equation. So let's say if f of x is equal to x squared minus 4x plus 4. And I want to find out the remainder when I plug in x minus 2, when I divide x squared minus this polynomial. Let's say that if this is our function, what's the remainder when I divide this function by x minus 2? Well, once again, I would just plug in the opposite of, in this case, negative 2, which is positive 2. So then I get f of 2 is equal to 2 squared, that's 4. Negative 4 times 2 is equal to, that's going to be equal to negative 8 plus 4, and I'm going to get 0. The remainder of this polynomial, when I divide it by x minus 2, is going to be equal to 0. And notice something pretty weird, right? So I can actually factor this polynomial to be x minus 2 squared, right? X minus 2 times x minus 2, right? Two numbers that multiply out to be positive 4 and add up to be negative 4 are negative 2 and negative 2. And if I divide this by x minus 2, and notice how we have a remainder of 0, right? Because this cancels out. So if you use the polynomial remainder theorem and you get 0 as your remainder, that means that it's a factor of whatever polynomial we have, right? So just know that when you're using the polynomial remainder theorem, right, if you plug in f of c and you get a remainder of 0, that means that it's a factor of f of x. Because once again, right, this connects the polynomial remainder theorem and the factor theorem. They're pretty closely related. So with factor theorem, remember, if x minus c is a factor of f of x, then f of c is equal to 0. And in this case, right, this is kind of like the same, it's kind of like the same process, right? If you want to find out the remainder, x minus c, plug in f of c, and the result will be your remainder. And if the remainder is 0, well, that means it has to also be a factor of it, right? I know I'm yapping a lot, but this is kind of just a quick summary of everything we learned. So if we have f of x divided by x minus c, well, if f of c is equal to 0, that shows that x minus c is a factor of f of x. And it also shows that 0 is the remainder of the polynomial when you divide it by x minus c. So I'm just like referring to like the factor theorem and the remainder theorem, polynomial remainder theorem. And let's say if f of c is not equal to 0 when you plug it in, let's say if it's equal to 87, this means that x minus c is not a factor, and that means that the remainder in this case is 87. Let's say if we have the function f of x is equal to x to the third power minus 4x to the second power minus 7x plus 10. Now, what if I wanted to find out the factors of this polynomial? How would I do this? If this is the only information you have, how would you do this? Well, one way to do this, if you have a graphing calculator, this is actually really easy, because all you have to do is just plug in your polynomial into your calculator, minus 7x, and you get that negative 2, 1, and 5 are the zeros of this polynomial. So negative 2, 1, and 5 are the zeros of this polynomial. And this means that x plus 2, x minus 1, and x minus 5 are the factors of this polynomial. Notice how when I put the when I go from like the zeros to kind of the factored form, right, I always write it like the opposite way, right? This 2 turns into a negative, this negative 2 turns into a positive 2, because negative 2 plus positive 2 gives me 0, right? This positive 1 becomes negative 1, because positive 1 minus negative 1 gives me 0, right? So it's kind of like when you're converting from 0 form to the factored form, well, it's always going to be like the opposite of what you're expecting to do. But what if we didn't have a graphing calculator? So the rational root theorem is a theorem that helps us do this, without a graphing calculator. What you basically do is you look at the constant term, so the term without an x, and you're going to list out the factors of the constant term. So what are the factors of 10? Well, some of y'all might be saying that's obvious, right? It's 1, 2, 5, and 10, right? But don't forget that factors can be negative as well, right? For example, negative 1 times negative 10 gives me 10, right? And negative 2 times negative 5 gives me 10 as well. So the factors of 10 are actually plus or minus 1, plus or minus 2, plus or minus 5, and plus or minus 10, all right? Don't forget that it can be negative as well. Now, what you're going to do is you're going to take the factors of the constant term, which is represented as p, and you're going to divide it by the factors of the leading coefficient, which is q. The leading coefficient is so what you're going to do is you're going to look at the term with the highest power. In this case, x to the third power is my highest power, right? I'm going to take a look at the coefficient in front of that. In this case, I have 1. So the leading coefficient is going to be 1, and the factors of 1 are going to be plus or minus 1. Sorry, this part I should put by q the factors of the leading coefficient. Sorry about that. So you're going to divide the factors of the kind of the last term by the factors of sort of the first leading coefficient, right? So yeah, we can either have plus or minus 1 divided by plus or minus 1. We can either have that, or we can have plus or minus 2 divided by plus or minus 1, or we can have plus or minus 5 divided by plus or minus 1, or we can have plus or minus 10 divided by plus or minus 1. So you can think about it as there's kind of 4 cases to this problem, right? If you have plus or minus 1 divided by plus or minus 1, that's just going to give you plus or minus 1, right? If you have plus or minus 2 divided by plus or minus 1, you're just going to get plus or minus 2. Same thing with the plus or minus 5, right? And the same thing as plus or minus 10. So what this is basically telling you are these are some of like the possible roots of the polynomial, right? These are the possible roots of the polynomial. It's saying that you either have -1, 1, -2, 2, -5, 5, and -10, 10 as the roots of a polynomial, right? So this theorem is nice because instead of randomly guessing a number that could be like a factor of this polynomial, well, now you kind of have a couple options to choose from that could be the factor of this polynomial. So in this case, let's say I pick -1, okay? If the root of this polynomial is -1, that's what it's basically saying is that x plus 1 is a factor of this polynomial, right? X plus 1 is a factor of this polynomial. So a way to figure out if this is a factor of this polynomial is by the factor theorem, right? The factor theorem. I'm just going to put ft. And remember, if you plug in, if you have x minus c, and you're trying to find out if this is a factor of f of x, well, just plug in f of c, and you're going to get the thing. So in this case, if I'm trying to find out if x plus 1 is a factor of this polynomial, well, I'm just going to plug in -1 into this polynomial. So f of -1 is going to be -1 minus 4 times -1 squared is just +1, minus 7 times -1, that's +7, plus 10. And this is equal to the 17. This is just going to be equal to 12. Now, because this number right over here is not equal to 0, this means that x plus 1 is not a factor of my polynomial. So yeah, that's the annoying thing about like the rational root theorem, is that not every number from here, obviously not every number from here is going to work, but it saves you from like randomly guessing like from the realm of all real numbers. So it makes things quite a bit more efficient. So if I want to find out if the root 1, aka if I want to find out if x minus 1 is a factor of this, well, I would just plug in f of 1, right? So f of 1 is equal to 1 minus 4 minus 7 plus 10, and I get 0. And that means that x minus 1 is a factor of this polynomial. And once you find out what's one root, and once you found out what's one factor of this polynomial, you can just stop right there and do synthetic division to simplify things. What I mean by that is, because we know x minus 1 is a factor of this polynomial, well, let's divide this polynomial by x divided by 1. So once again, we're going to use synthetic division. Our coefficients are 1, -4, -7, and 10. And I'm going to put this 1 to the side, right? Because 1 is what makes x minus 1 equal to 0. And now I'm just going to do synthetic division. So I'm going to bring out this 1, multiply. I'm going to add this up together. So I'm going to get -3, multiply. I'm going to get -10, multiply. And notice how I have a remainder of 0, which tells me that this is a factor of it. So everything's going well. So now I have x squared minus 3x minus 10. And because I want to find out the roots of the polynomial, right? I want to find out the factors of it, right? I'm going to set this equal to 0, right? This is going to be set equal to 0 because I want to find out the factors of it. So now what I have to do is I can either use the quadratic formula, or I could just look for two numbers that multiply out to be -10 and add up to be -3. And that combination is -5 and +2, right? And there we go. So that means that the factors of this polynomial are x minus 5, x plus 2, and finally x minus 1, right? So f of x is equal to x minus 5 times x plus 2 times x minus 1. The final concept here is the imaginary unit. So you might be thinking, how can you take a square root of a negative number, right? Because you've probably taken square roots, you've definitely taken square roots of like positive numbers, right? Because a positive number times a positive number gives you a positive number. And a negative number times a negative number gives you a positive number. So how can anything inside the square root be negative, right? Try to find two numbers that multiply out to be -1. Two of the same number that multiply out to be -1. And you can't, right? It seems impossible. But the imaginary unit was created and all of a sudden it became possible. If you multiply I by itself, aka I squared, you get -1. The way to visualize this is if I is equal to the square root of -1, well, if you square both sides, well, then the square root and this cancels out, right? So I squared is equal to -1. I to the third power, you can think about this as, we know that I to the third power is equal to I to the second power times I to the first power. This is due to like property of exponents, right? If the base is the same and like the exponents add up to be the same, well, it's okay. I to the second power we know is -1, and I to the first power we know is I. So -1 times I is -I. And finally, we have I to the fourth power. I to the fourth power can be represented as I to the second power times I to the second power. And we know I to the second power is -1, so it's just -1 times -1, which is just +1. And these are the only I kind of powers you need to know. The reason why you don't have to memorize like things like I to the fifth and I to the sixth is because they're always going to be a repetition of one of these values. For example, I to the fifth can be written as I to the first power times I to the fourth power. And the reason why you want to use multiples of 4 is because I to the fourth power is equal to 1. So this kind of just like cancels out, right? Because if you're multiplying 1 by whatever, right, you're going to get the same thing. So you're just going to be left with I. If you have I to the sixth power, this can be written as I to the fourth power times I to the fourth power. Times I to the second power, sorry. I to the fourth power is 1, and I to the second power is -1. -1 times 1 is -1. So you notice how it's just like a repetition of the values that we already know. So, no need to memorize these. If I had something like I to the 129th power, how do you solve this? Well, you can rewrite this. All right. So the hack for doing this type of problem is whenever you have I raised to the, let's say the 10,039th power, all right, the only two numbers you need to focus on is the last two numbers. All right, so it's like you can ignore all of these numbers in the front and you only focus on the last two numbers. So I to the 10,039 can be rewritten as I to the 39. They're equal to each other. And the reason why is actually pretty straightforward. See, let's start off with a simpler example. Let's say if we want to find out the answer to I to the 129th power, right? So what we can do is we can rewrite this as I to the 100th power times I to the 29th power. And I to the 100th power, because 100 is a multiple of 4, right? You can all agree that 100 is a multiple of 4. And whenever you have I to the multiple of a 4, you're going to get 1, right? We said that I to the 4th power is equal to 1. And it turns out that any multiple of 4, like for example, I to the 8th power, right? I to the 12th power, any multiple of 4 for I is always going to be equal to 1. Any multiple of 4 that, the I power is kind of like the I is raised to, it's going to be equal to 1. So that means that if I to the 100 is a multiple of 4, that means that if 100 is a multiple of 4 and you're taking I raised to 100, well, this is just going to be equal to 1. And it turns out that 1,000, 10,000, all of these are multiples of 4, meaning that you only have to focus on the last two digits because the first 10,000 digits are just going to be equal to 1. So I to the 29th power, well, then this gets pretty simple, right? We can rewrite this as I to the 28th power times I to the first power. 28 is a multiple of 4, which means that it's just going to be 0, and you're just going to be left with I. So I to the 129th power is equal to I, just regular OI. If we have something like I to the 456th power, remember what we do? The hack is you only focus on the first two numbers. The last two numbers. So it's just going to be I to the 56th power, and 56 is a multiple of 4, meaning this is just going to be equal to 1. So a little bit more about I. So complex numbers are numbers that can be written in the form A plus BI. So A represents the real part, and then the BI part represents the imaginary part. For example, if I have something like 3 plus 4i, right, that's an example of a complex number. Even a number like 3, right, a number like 3 is actually a complex number, believe it or not, because it can be written in the form A plus BI. You can rewrite this as 3 plus 0i, right, and this is a complex number. The number I itself, let's say 2i, right, this can be represented as a complex number because you can rewrite this as 0 plus 2i. So kind of the main point I'm getting here is that all real numbers are complex numbers, and all imaginary numbers are complex numbers. So yeah, that's the key thing to note. Now, just like how in math, right, you rationalize the denominator. For example, if I have the square root of 2 divided by the square root of 5, the thing like mathematicians don't like is they don't like square roots, radicals in the denominator. So what they'll often do is they multiply the top and the bottom by the denominator in this case, by the denominator in this case, so that this square root of 5 times square root of 5 cancels out to be just a regular 5, and you get radical 10, right? And if you're let's say dealing with something like the square root of 3 divided by 3 minus the square root of 5, how would you get rid of the denominator in this case? Well, you would actually multiply the top and the bottom by something called the conjugate of this denominator in this case. So the conjugate is just when, it's basically just the same thing, except you change the sign of the radical. So if the radical was negative before, it just becomes positive. That's just the conjugate. There's not much else to it. So you're just going to multiply the top and the bottom by this conjugate. 3 plus the square root of 5, and then 3 plus the square root of 5. Now you're going to have to FOIL this out. You can use the difference of two squares, but just to show every step, I'm just going to FOIL it out. So 3 times 3 is 9. 3 times the square root of 5 is 3 radical 5. But the thing is, you have 3 times the negative square root of 5. So these two things, they cancel out. So it's just going to be 9 plus, and then the negative square root of 5 plus square root of 5 times square root of 5 is, so negative square root of 5 times, and then the negative square root of 5 times the square root of 5 is just going to be negative 5. So 9 minus 5 is going to be 4. That's going to be our denominator, right? And then in our numerator, it's just going to be square root of 3 times 3 is 3 radical 3. And then the square root of 3 times the square root of 5 is just going to be times radical 15. And boom, you gotten rid of the denominator in the bottom, right? You gotten rid of the radical in the denominator. And it turns out that you actually do the same thing for imaginary numbers. So just like with radicals, mathematicians, they don't like to have a denominator with I in it. So what they'll often do is they multiply this using the complex conjugate. And what is that? Well, it's just the same thing as before. It's literally the same thing, except you switch the sign of the imaginary thing. So if the sign of the imaginary part was negative, just change it to positive. And then you just multiply the top and the bottom by it. So 7 plus 5i All right. Now we just have to FOIL everything. So 7 times 7 is 49. And you notice how this negative 5i times, this 7 times 5i and this negative 5i times 7, they cancel out, right? Because it's a difference of two squares. And negative 5i times 5i is just going to be negative 25i squared. We said I squared is equal to negative 1, so we can substitute that in. So we can get times negative 5 times negative 1. These two negatives cancel out, and you get 49 plus 25. In this case, that's just going to be 74. And in the and in numerator, well, you got 2 times 7, that's 14. 2 times 5i, that's going to be plus 10. 4i times 7, that's going to be 28i. And then 4i times 5i is just going to be 20i squared. I squared is negative 1, so it's just going to be equal to negative 20. So minus 20. So in this case, our numerator, well, all we have to do is kind of combine like terms. So this 10i plus 28i creates 38i. And then this 14 minus 20 is equal to negative 6. And this is correct, but we're not done yet, because it says for us to put this expression in a plus bi form. So we want the real part on one side and the imaginary part on the other side. So what I'm going to do now is I'm just going to break this off into a fraction, two fractions. It's just like how, if you have, let's say, 2 over 4 plus 3 over 4, right? Because they have the same denominator, you can add numerator together. Well, you can also go backwards, right? And in this case, we're going to go backwards. We're going to be like, okay, let's separate this fraction into two parts. We have negative 6 over 74 plus 38i over 74, right? So now we separated the real part from the imaginary part. So 6 and 74, they have a common factor of 2. So this simplifies out. So we have negative 3 over 37 plus, so 38 and 74, these two have a common factor of 2 as well. So plus 19 over 37. And don't forget the I. And there we have it. This is our simplified expression in a plus bi form using the conjugate method.